Hello and welcome back to Calculus 1, section 3.11, related rates, part 2. So we have a few more problems to discuss. As I said, this is a very important section. It's applied and you can actually make a living doing this stuff. So we're taking the derivatives in respect to time. We want to see the change involved in time, and most of these problems are related to some kind of a geometry. And then we let it change in time and grow. And we measure that with the derivative that it's taken in respect to time. So now let's watch a launch real quick.
Falcon 9 lift off a beautifully clear shot there at 4.50 plus 10 seconds.
That is actually what I'm going after, a beautifully clear shot. All right, that's what I'm going for. Observe that the rocket is in the middle of the shot. It's going 1,000 miles per hour currently, and it's speeding up. So you see the kilometers per hour divided by the 1.6 to get the miles. So yeah, that's that.
Coming up about 50 seconds from now, there'll be 3 events in quick succession. The main engine will cut off, separate, second stage will start its Merlin vacuum engine. So what you heard is just getting its own chills.
It's pretty, doing 5,000 kilometers per hour. So this is the best we can do as a species, and it's still nothing. Maybe one day.
Cut-off happening in just a few seconds from now. Good. Some of the flicker from Merlin vacuum engine fluid as it flickering the cameras that was actually interacting with the top of the interface there for a moment. Our next major event is the fairing deploy coming up just a few seconds from now. That's the second stage of deploying fairing.
All right, so I mean, this video is now beyond what I needed it for. What I wanted to explore is this, right? So the shot, right? The shot following this rocket. This is not a Joe standing on the side of the camera, like following it. This is actually motorized. So I would like to develop some kind of equation that we can program into the controller so that controller can turn the servo motor, which will keep the rocket in the center of the shot at all times. Right? And humans can't have that precision and that much of a steady hand or any of that stuff. So let's go to our lecture over here, all the way at the bottom, and say that we are designing this system. We're going to have some kind of bunker for the camera. And there's going to be a launch pad over here with a rocket. Looks like a missile, but that's okay. The rocket is going to shoot straight up, and we want to make sure, so at first, right, that's the shot, and then it will follow. Now, when I say the shot, obviously the camera has the field of view, right? So I draw the middle line that hits the middle of the rocket, but the camera always has the field of view like this, and then eventually it will have the field of view, right? So that's something that it's important to understand. So, right, we take just these few lines here. Now, we want to measure the speed of the rotation, right? Because there is a hinge over here and the motor, which will slowly turn the camera, right, up, so as it goes to follow the rocket as the rocket goes up. So there is this circular motion in physics known as angular velocity omega, which is measured in radians per second or radians per minute, or revolutions. You can also do that per minute. The RPM, revolutions per minute, right? In your car you have 800, right? When it starts redlining, you want your revolutions per minute to be between 1,000, 2,000. When it's idling, 700, 800. So we want this omega. Now that omega is change in this angle here, which clearly changes because we change the angle of the camera to shoot the rocket from its standard position going up, right? And then what I have here is I have the height, and I have this distance. Generally, when I teach this problem, I use 500 feet, but you can use whatever you want, right? So what is the geometry that I have? What's the geometry? Right triangle. So I have geometry as a right triangle. And then which concept are we going to use now? We have area, we have trig, we have perimeter, we have the Pythagorean theorem. So which concept are we going to use to connect the three things that are given in the triangle that we are observing? Yeah, it will be the trig. So now, which of the trig, or which two of the trig would connect the angle with this one, with this one? Tangent. Very good. So we are writing that the tangent theta is equal to opposite, which is height, divided by the flat 500, which is adjacent. And now I can move 500 to say that the height is equal to 500 tangent theta as the equation, and hit this with the time derivative to see what I can get. So dh dt is equal to 500. Derivative of tangent is? Very good. Secant squared theta and then we have d theta dt. Now I'm just going to, circle this, and I say this is your omega from physics, angular velocity. That's what we are after, which means that I have to kick the other two things to the other side. So I have 1 over 500 secant squared theta dh dt is equal to d theta dt, which is what I'm after, which is omega. So now d theta dt is equal to, now secant squared in denominator goes up as what? Very good. Divided by 500 dh dt. So this is my, math related rates. But for purposes of, what we actually are calculating, it's cosine squared theta divided by 500 dh dt. What is dh dt? What's dh dt? As a concept in the problem, what's dh dt? No, that was omega. Yeah, change of height in time. Yeah, what's that? Yeah, but what is that? Velocity. It's the speed of the rocket. Do we have that? Yeah, we do. 1,579 kilometers per hour. As you're looking at this, right, video. You have the timestamp, you have the time, you have the speed, you have the distance as well. The 12.5 kilometers. So if you need age, you have it, 12.5. If you need the speed, you have it, 1,579. No matter where we are in the video, I have that information. So when I go back here to look at my calculations, I have cosine of the angle, which we can measure because that's on the camera. And then we have how fast the rocket is moving. As you keep feeding those as input to your software, that the software will be computing the speed, which is the RPMs at which the motor should be turning the camera so that rocket is always in the middle of the shot. Right? This is how you design things. And all you need to do now is to get the controller, right? Put this equation, well, you have to write the software for it, obviously. You put this on the controller and then connect the power to the controller, connect the power to the motor, and then let the controller control the servo part of the motor, and that's it. The camera will turn. This is a very simple thing to design. However, obviously without these calculations, you can't program the controller, so everything else is useless. Now, you don't really have trials to do this, right? You say, oh, I'm going to do the guess and check method, right? So, and then I will adjust it to time. No, there is a launch and that's it. And if you missed it, right, you missed it. And no one's going to, hire you to go there and have your trial and error, for 100 launches missed that you don't have on the video because you're not able to get the simple equation and program that onto the controller. So that's that part, right? Another batch of again, the rest is plug in the numbers. You have the speed of the rocket, I said, and you have the angle. So you plug those two numbers in and you get your omega. The units over here would be radians per second, let's say. radians per second. Right, that would be units for angular velocity. Angle is measured in radians or degrees, but radians. So let's first talk about volume formulas. No. We are going to learn all of the volume formulas that exist. There is no formula sheet on the test, and you need to know the cone and the sphere and the cylinder and right, so all of them. And we can learn all of them easily by placing them into these three categories we are going to have. So, category 1 are prisma. So prism-like object. The next one I call pointy or spiky. Pointy. And then sphere as the queen of all of them. So sphere has its own category. It doesn't belong to anything else because sphere is the perfect object, right? Sphere is the most perfect object that exists in the 3D realm. So let's take a look at it. So prism. Prism-like objects would be something like a box or a cylinder. And all of their volumes are given as B times H. Area of the base times the height. So if you know what is the base, so you look at this room, we are sitting in an octagon, right? I mean, the object that it's built on the octagon. Technically, what you have on the floor is the stop sign, right? It has 8 sides. If you know the area of the floor, the octagon, you can multiply it by the 10 feet, the height of the ceiling, or 12 feet, whatever this is, and you will have the volume. So whatever has these edges to rise straight up, and you have the same bottom and the same top, and those are parallel, the volume is simply whatever the area of the base is times the height. Then we have the pointy or the spiky objects, and those would be cone and pyramids and things like that. So I can have a 4-sided pyramid, or the cone, right? The witch's hat. Well, you need to add a little bit to it, but it's a cone. And these guys are, volume is 1/3 B times H. So that's all it takes. So now, please observe that if I have a cube, right? If I have a cube with side A everywhere, volume is A cubed. If I have a pyramid with side A, is just 1/3 A cubed. All right? So, well, given that the height is A as well, right? So that's what it takes to learn. So my question to you is now, do you know area formulas? You are not supposed to concern yourself too much with volume formulas. You see that it only, the only important thing over here is the base. And then you multiply that by whatever the height is, right? I can make a pyramid out of the trapezoid. Do you know the area of the trapezoid? Right? So if you have a trapezoid in the area, right, and then you build a pyramid on top of it, right? So the pyramid would look something like that. Let's say it's something ridiculous, but yeah. So the spike is coming out of the screen, right, directly at you. This thing will have A, B, and the height h, and then you need to know that the area, which we use, well, we'll call that capital B, base, right? Area of the base is A plus B divided by 2 times the height of the base. And then if it's a pyramid object, it will be 1/3 base times the capital height to come up with this thing, right? And then we have the sphere, ball, right? Volume is 4/3 pi r cubed. Yeah, you just have to memorize that. Now, why is this perfect? Because if you take the derivative of it in respect to radius, you're going to get actually surface area. It only works for sphere. The same thing like it only works for circle to take the derivative of area and get the perimeter. Right? Those are perfect objects. Right? Circle and sphere. Circle for 2D and sphere for 3D. Guys, these are all of the volume formulas that exist in the galaxy, right, for the problems. So you're not learning these one by one. Well, of course, you're learning one by one for a sphere, but that's the only one. The rest is it spiky or not? If it's spiky, it's 1/3 times, right? That's that. So now you know all of them. And, you know, with this list, you can attack any problem that is given to you in the book, right? Any geometry of this. Now, obviously, the requirement is that the ceiling and the floor are parallel and the edge walls rise straight up for the first one. The second one has to end in a spike. And then the sphere is the sphere, which you should be familiar with. So now, we can have a snowball tossed right there. We have to have a house, have to have smoke from the house, windows, and door. There we go, perfect, with a handle, right? We are going to have another person over here, because we need the victim as well. To put the hat, little thing on top, and the scarf. Now this person is not paying attention, obviously. See, the feet are going towards the house. We drop the snowball, and we all know what happens. Sounds good? So what would be the problem? What would be the problem in this case? Well, you want to see, you know, how large is this snowball going to grow as it goes, right? So what is it accumulating as the time progresses? What is accumulating? Mass. What else? What else? Size, which is related to radius, and I'm still looking for the volume. Thank you. There we go. So yes, mass is related to volume, and the radius grows, volume grows, right? And also the speed and all of that kind of stuff. So volume is 4/3, well, 4/3 pi r squared, same thing, but 4/3 pi r cubed. Did I say squared? Take the time derivative here, and we will have that the change in volume, which is the growth factor of the snowball, obviously, is going to be 4 pi over 3 times 3r squared dr dt. 3's cancel, and we have our dv dt, which is the formula which measures how fast is the volume changing. Related rates. Now this belongs to the vanilla pile of problems, because you know the sphere formula. If you don't know it, you will know it by Thursday, obviously, if you care. So you have the formula, you differentiate that formula, and you plug the numbers that are given. If the radius of the snowball is increasing at the rate 1.7, and the radius is, I don't know, 1.2 feet, right? How fast is the volume changing? Great, I just gave you dr dt, and I gave you r, you plug those two numbers, and you get your dv dt. So the key for these problems is to read carefully, and from the text, pick up which variable, right? Which variable is which, and just plug everything in, and then that's it. Sounds good? Questions, concerns? Too easy? Yeah, of course, when I do it, it's easy. Try homework, it's hell on earth. We'll see. So please make sure you do a lot of these problems by tomorrow. So today, do a lot of these problems so that you can ask questions and have time to think about answers and learn answers and learn the methods that these problems are done, because, guys, tomorrow is Tuesday, right? So if you bring your questions on Tuesday, you still have Wednesday to kind of work through those concepts. Do not put this off all the way to Wednesday because exam is Thursday when you're going to ask questions. I hope you talk to your TA, and he's going to be there, right, to help as well. We are going to have review on Wednesday, but we also have to do some of the new stuff as well. So chapter 4 is application of derivatives. So we will start tomorrow 4.1 and 4.2. But before I do 4.1 and 4.2, I need to ask you guys about the questions from this section. So we'll probably do 1 or 2 problems. I mean, we'll do nothing if you don't have questions, obviously. But if you do have questions, then we'll do this first. And then we'll move on into chapter 4, which is still derivatives, but now they're applied derivatives. So we'll be looking for min and max, and you'll read that stuff on your own. All right, well, that's it for today for lectures now, lab time.